Hi everyone, welcome to our 8th lecture of CSC 110. In this lecture we're going to be studying operating systems and a little bit on hardware and encryption. Okay, so what is the operating system? It's arguably the most important piece of software that's in a computer, and we're going to be looking at it in depth and what it does for you. But before I even jump in and start talking about the operating system, I have to tell you what the distinction is between hardware and software, because the operating system is a kind of software, but then there's the other part of the computer, which is the hardware. Okay, so what do we mean by these terms? Okay, now the distinctions that I'm going to be making in this lecture are important, and the reason is that when you go out and you buy a computer, you want to know what you're getting. Okay, and so you want to ask questions about its hardware. So what kind of components are inside this computer and what can they do for you? Okay, but you also want to ask questions about its operating system, because that'll also have implications about what you can do with the computer and what you can't. Okay, and so this whole lecture is really geared towards being informed about what you're going to be getting when you buy a computer. Okay, in terms of its hardware and software. All right, so like I said, before we jump in and start talking about the operating system, I got to tell you what the hardware is. Okay? So hardware means the physical components of the computer itself. Okay, what you can actually touch. Now, you can think of the hardware at two different levels. What we did earlier in the course when I designed for you that adding machine, I showed you how you can build an adding machine ultimately at the lowest level in terms of transistors. Okay, and the way these things are manufactured is, those transistors, they're actually etched onto a silicon wafer. The transistors are incredibly small. They're so small that you can't see them. Okay, and in fact, they're smaller than a human cell, if you recall. And they're etched onto this silicon wafer, and then the silicon wafers get caught up and they get glued into these integrated circuits, and the integrated circuits get placed onto motherboards, and that's what you see if you would open up your computer. Okay, now once the circuit has been etched onto a silicon wafer, it's not like you can go in there and change the circuitry. Okay, that's been hard coded into that silicon wafer, and that's something you just get when you get your computer, and you're not going to be able to change it. Okay, so in that sense, this is hard. Okay, it's hardwired or hard coded or something like that. When we say the word hard, it means unchangeable. All right, you simply can't add more functionality to the computer by changing its the circuitry on these integrated circuits. Okay, now if you did open up the computer, especially a desktop, by removing the side panel, there are some components that you can remove and then add. Okay, they're usually known as cards, like a graphics card or a PCI card or something like that. So there is a little bit of configurability to the hardware. Okay, for instance, especially if you're into gaming, you can remove a graphics card and put in a new graphics card that might give you more functionality, and so you could make hardware changes at that level. But it's not like you can go into the graphics card, into those integrated circuits, and start rewiring the integrated circuits to give you different kinds of functionality. That's not the way a computer works. Okay. And so this hardware is like I said, impossible to change, and it's just what you get. The changeable part of the computer, that's the software, which we'll talk about in a little bit. Okay, but let's finish off our story on the hardware, because I want to show you what kind of components there are inside a computer. So if what I did earlier in the course, when we looked at the circuitry right down to the transistors, if that's the microscopics of the computer, what I'm going to be doing now is the macroscopics. Okay, and if you want an analogy, say, to the human body, what we were doing earlier was kind of like cell biology, looking right down to the lowest level functionality of the computer. And what I'm going to be doing now is like a gross anatomy. What would you physically see inside of a computer if you opened up the panel, and what do those components do for you? Okay, the most important piece of hardware in the computer is the so-called CPU. Okay, it stands for Central Processing Unit. It's the brains of the computer. Okay, and this is where all that circuitry is that does the actual calculation. And in fact, it's done in a particular part of the CPU known as the Arithmetic Logic Unit, the ALU. Okay, so all that kind of addition that we talked about earlier, and those gates and all that, they live inside of the ALU, and the ALU does all the kind of computation, all the real deep thinking that a computer does. Now, that's still a small part of the CPU. There's more parts of the CPU, and those other parts of the CPU have to do with efficiently running the machine by getting instructions and then executing those instructions, carrying out orders from the software. Okay, I don't want to get into that because that's beyond the scope of this course. But there's a lot of things that the CPU has to do beyond just the kind of logical operations that we talked about earlier. Okay, now when you go out and you buy a computer, you're buying that CPU. And you might ask yourself, well, what can the CPU do for me? Okay, like what kind of choices can I make? All right, and there's a few choices here. Okay, so probably the most important choice that you need to know about is what family of CPUs does your CPU belong to? Okay, if you're purchasing a CPU, you're saying, well, what family does this belong to? What type of CPU is it? And there's two that you should know about. There's the Intel family, okay, and also known as AMD, because they're named after two different companies, Intel and AMD. But they're compatible with one another, mostly, okay, not 100%, but almost 100% compatible. Okay, so we can call it Intel architecture or AMD architecture, okay, and that's what most laptops and desktops use. Okay, they use an Intel chip or an AMD chip. All right, and there's two different types. There's the newer ones, which are the 64-bit Intels. Okay, and almost every single computer today is a 64-bit Intel. All right, there are the older machines, but they're so old now that you may not even come across one. But if you had a machine which is about 10 years old, there is a chance that it might actually be a 32-bit Intel. Okay, but like I said, most machines today are 64-bit Intel. All right, and by the way, that 64 and 32 bits, that's how many lines there are in that ALU. So you remember when we designed the adding machine that I designed for you could only add up to 4 bits, okay, because I didn't want to make it too big. But in older computers, 10 to 15 years old, they could add up numbers which were up to 32 bits in width, okay? And the modern machines, which you would purchase today, can add up to 64, okay? And so, there are two architectures, but related to one another, the 32-bit Intel and the 64-bit Intel. And the 64-bit Intel is backwards compatible to the 32-bit, okay? And when we say that, we say, well, what do you mean by it's backwards compatible? So these CPUs, they're running these instructions, okay? Think of it like a language, like a human language, okay? And the 32-bit was a particular language, okay? And the 64-bit covers all of the 32-bit and more, okay? So it's like the 64-bit has an expanded instruction set over top of the older instruction set. So there's this backwards compatibility, okay? This language that the CPU actually runs or understands is known as the ISA, or the instruction set architecture, or sometimes we'll just say architecture. Okay, so when I say 64-bit Intel, what I'm saying is that this particular CPU, if I say this CPU is a 64-bit Intel, I'm saying that this particular CPU knows how to run 64-bit Intel instructions. Okay, that's the language it speaks. All right, and if I said to you 32-bit Intel architecture, I would say that this CPU runs 32-bit Intel architecture. All right, the 64-bit Intel will run the 32-bit Intel architecture. The 32-bit will not run the 64. Okay, so it's backwards compatible, but not forwards compatible. All right. The other family of CPUs that you should know about are the CPUs that are in your phones. And these are known as ARM architecture, okay? ARM. And just like there's a 32 and a 64-bit Intel, there's also a 32 and a 64-bit ARM, okay? And they're not forwards or backwards compatible. So even though they're both called ARM architecture, and they're not really related to one another, okay? So that probably wasn't a good name to give them the same name, because people will think that 32-bit might run on 64-bit, just the way 32-bit Intel runs on 64-bit Intel. 32-bit, you might say, well, maybe 32-bit ARM runs on 64-bit ARM. No, it doesn't. Okay, it doesn't. So 32-bit ARM will not run on 64-bit ARM, and 64-bit ARM will not run on 32-bit ARM. Okay, they are totally different architectures. Well, I wouldn't say totally different, but they certainly are not compatible. Okay, so once again, just understand this compatibility. 32-bit Intel architecture, okay, that language, 32-bit Intel, will run on 64-bit Intel CPUs. Okay, but 64-bit Intel architecture will not run on 32-bit. So the 64 is backwards compatible. Okay, it understands the older language. All right. The 32 and 64-bit ARM, they're totally incompatible with one another. All right. So, this says a little bit because later when I show you operating systems that you could install, not that you would probably do this, you usually buy a computer with the operating system, but if you were to install an operating system, you'd have to ask, well, what kind of a CPU do I have? And if you have a 64-bit Intel, then it would run 64-bit Intel. Okay. It would also run 32-bit Intel. All right. And so you could install either one of those. All right. But if it's ARM, you have to get the right one. So if it's 64-bit ARM, you have to install 64-bit ARM. Okay. So there we go. There's 4 different families of CPUs. Okay. And what else do you need to know about a CPU? The other thing you should know about CPUs when you go buy them, especially if this is a laptop or a desktop, okay? Although it's true also of phones, and it's becoming more true of phones as phones become better. It's how many cores they have, okay? So most CPUs today are, I should say, really computers, okay? They come with either 4-core or 8-core CPUs, okay? Or and in addition to that, 4 or 8 thread CPUs. You say, well, what's this core and what's this thread business? Okay, so because CPUs have been shrinking so much, even though there's one integrated circuit, which we call the CPU, it's really made up of multiple cores. Okay, and I'll show you a picture of a CPU in a minute. But it's one integrated circuit, but it can have multiple cores. Okay, now if the CPU that you buy has 4 cores, that's really like 4 processing units in there. Okay, well, you can also buy a CPU with 8 cores. Well, think about it, that does twice as much computation. All right, it doesn't mean that it'll necessarily run twice as fast, but it does mean that you can run twice as many things on it without it loading up the CPU very much. Okay. And then there's this business of threads. Now the cores, they really are independent of one another. Okay, the threads are not quite independent, but they allow a little bit of what's called parallelization. Okay, and it means it allows more than one program to run at the same time. The bottom line is, if you're buying this, a computer with different CPUs and you want to compare them, okay, the cores are better. More cores are better than more threads, okay? But you can have multiple cores and you can have multiple threads. So you say to yourself, well, which one's the better CPU? And obviously the 8-core is better than the 4-core, okay? But you might also be comparing 2 CPUs, and one has 4 threads and the other one has 8 threads. And of course the 8 threads is better, but if you really want the fuller form of parallelization, look at the number of cores, compare the number of cores before you compare the number of threads. Okay, so I hope I made that clear. In other words, multiple cores is better than multiple threads. Okay, although as you increase the number of cores or you increase the number of threads, you increase the possibility of this CPU to do multiple tasks at the same time. Okay. So that's another thing. It's like how much parallelization there is on this computer, okay, on the CPU. And the other thing that you can compare is the speed, okay, and that's just how fast it does computation. And this is actually measured in gigahertz, all right. So, like if you have a computer with a CPU that runs at 2 gigahertz, okay, that's going to run at half the speed compared to a computer that has a CPU that runs at 4 gigahertz. All right, so roughly speaking, things would happen twice as fast on 4 gigahertz than 2 gigahertz. Not totally, and the reason is because the computer is very complicated and there's more stuff going on than just what the CPU is doing. But if you're just looking at, just raw computational power, 4 gigahertz is twice as fast as 2 gigahertz, okay? Now today, most CPUs are between 2 to 4 gigahertz, okay? And so, that's the range you're going to be looking at, and you choose, generally speaking, 4 gigahertz is fast enough. You probably could live with even 3 gigahertz. Like there are 3.2 gigahertz machines, and between 3.2 and 4 gigahertz, you probably won't notice the difference, and it might make a difference in the price. Okay, but those are the kinds of things you're looking at. So just to repeat, the first thing you want to look at is what family of CPU. Okay, and if it's a desktop, laptop, 64-bit Intel. Okay, if it's a phone, the 64-bit ARM is better than the 32-bit. Okay, the other thing you want to look at is how much parallelization there is, and for that, first compare the number of cores More cores means more parallelization, and then after that, if it has the same cores, then look at how many threads there are. Okay, and then the final thing to compare is the CPU speed. Okay, and that's in gigahertz. All right, so between 2 to 4 gigahertz. All right. By the way, gigahertz means billion operations per second. So a machine that runs at 4 gigahertz, that basically does 4 billion operations per second. Okay, that's like 4 billion additions in every second. You're not going to be able to do 4 billion additions in your entire lifetime, never mind in just a second. Okay, so computers run extremely fast compared to the human brain. Okay, there you go. This is the so-called CPU. Let me just show you a typical CPU price here. So what we're looking at right now is a site. This is a company, Tiger Direct, and there's others like there's Newegg and places where you can buy components of computers. This is mostly for people that want to put computers together. But what you're looking at here is a typical CPU costs about $320 here, and as you can see, it's an Intel. Core i7 is its name, all right, and you can see here that it is 8 cores. Okay, and so that's that's a measure of its parallelization. But in addition to 8 cores, it also is 8 threads. Whoops, 8 threads. Okay, so this is the highest level of cores and highest level of threads. All right, and then there's other information too, which I'll skip. But the last piece of information is the speed here, and that's right here, and it's a 3.6 gigahertz processor. Okay, so this is a fairly good processor. I think most people would be very happy with this, and that sells at about $320. Okay, now if you bought this, you go, well, what do I do with it? Well, it is just one component among other components in a computer. So you'd have to know how to put a computer together, and make sure that all the components fit. Like, in other words, you need a motherboard that this properly fits into. But if you know what you're doing, it's not that hard to put a computer together. I've put together dozens of computers in my lifetime from scratch like that. Okay. All right, so there's the story with the CPU. What's next? Well, the next thing is the storage unit, okay? So I want to call it a storage unit because nowadays there's so many different types of storage units that, it's not good to call them all hard drives because they're really not hard drives anymore. But in the old days, the very old days, these were platter hard drives, okay? And what they were is, like if you were to open them up, there's like a spinning platter. And the platter is magnetic, and then there'd be this head that would float on top of the platter as it spins. So the platter is spinning, and this head floats on top of it, and it reads the data off of that. Okay, these were the old hard drives, and that's why we tend to call these things hard drives. But there's other types of memory today. Okay, storage memory. Okay, and these are like solid state drives, and they're abbreviated as SSDs. And then there's SD cards. These are the cards that you like plug into, like into cameras or into tablets and things like that. Okay, there are also storage USB, your USB stick. Those are also storage and so on. Basically, storage is anything which is non-volatile memory. And what does that mean? So memory means it stores stuff. It stores information, and non-volatile means that when the power goes off, the information is not lost. Okay, volatile means it flies away. Okay, so this is non-volatile. Like when you unplug your USB stick, it's not like the USB stick has a battery inside of it. There's no power in that USB stick at all, and yet the information is still inside of it. Okay, and so any memory where when you power off the machine, the information is retained, so it's retained from power on to power on, okay, or retained over power off cycles. That's non-volatile memory, okay. And every computer has to have that because you got to have somewhere to store your files. Where are you going to save your files? Okay. Not only the files saved there, but the operating system is too, and all of the software, which we're going to discuss in this lecture. So you have to have a hard drive, some kind of a storage unit, okay. Now, typical sizes for hard drives, it depends on what you're buying. But if you're buying like the old style platter, okay, the discs, the actual old hard drives, okay, nowadays they're abbreviated as SATA, and they are they go for about 6 terabytes. They go for about $200. Okay. They're the slowest of all the hardware storage that we have right now. Okay, so 6 TB, that's a lot of data for only $200. So that's pretty cheap. So that's the advantage, is that SATA drives are cheap. Okay, and you get a lot of storage for very little money. But the disadvantage is that they're slow. Okay, that means that if your operating system is on one of these or any other software that you have or files, they start up pretty slowly. Okay, compared to the solid state drives. Okay, these are the SSD drives, and they don't have any moving parts. They're all just purely circuitry inside of them. Okay, and they're much faster, but they also cost more. Okay, so for a like a 2 TB drive, they're about $300. Okay, so you can see that that's significantly more expensive because you got only 1/3 of the storage compared to the 6 TB, and it even costs more money. Okay, they are worth it though because they're very fast. Okay, and you would experience a big difference between booting off of a SATA drive versus booting off of an SSD. Okay, and then there's the other things like like your phone, and your phone has what's called flash memory in it. Okay, and a phone's the flash memory is much smaller than the storage units for laptops or desktops. And so you can see here that a typical phone, like I just picked one at random. I picked the Samsung Galaxy A32. Okay, it's an upper, no, I wouldn't say upper. It's a mid-level phone at about $200, and it comes with 64 gigabytes of flash memory. Okay, that's how much you can store apps, pictures, everything before you fill up the memory on the on that device. Okay, now remember when you're comparing these numbers, a terabyte is 1,000 times bigger than a gigabyte. Okay, so here we're like, if you wanted to compare this number and that number, this is like 2,000 gigabytes compared to 64 gigabytes. Okay, so phones, they have much smaller memory units. Okay, and generally speaking, you don't fill up one of these drives very easily. You can, if you go crazy downloading movies and stuff like that, you can certainly fill them up. But like I said, generally speaking, it's pretty hard to fill up, a terabyte drive, or 2 TB or 6 TB. But it's not that hard to fill up a phone. Okay, most people have gotten to the point, I certainly have, where I've put enough apps on a phone that it says, you know what, you got to remove some apps. Okay, I just can't store anymore. Okay, or you run out of places for pictures. Or the other big one is if you use your phone to like take movies. Okay, little short clips of video, and if those start to add up, okay, then your phone is going to fill up pretty quickly. Okay, so there you go. That's what's known as storage. Okay, you'll often hear me say hard drive because I'm going to always fall back on the old language, but the proper name is storage. Okay. So let's take a look at some typical storage units here. So here we go. This is a SATA drive. So this is the old style platters. Now you can't see the circular disc that's in there, but if you were to open this up, it's like a box. If you were to open this up and you would look inside, you would see that there's a circular disc that's rotating. Okay. Now this is one of the Western Digital products. It's a very good disc. It's 6 TB and it's selling for it looks like about $190. Okay. So there you go. There is a storage unit. Okay. You need another kind of memory in a computer, and that's just called memory. Okay, this is also known as RAM. You might hear it called RAM for random access memory, but we'll just call it memory. That's its proper name, and it is volatile memory. Okay, and what that means, this is memory that disappears once the computer is turned off. You can go, well, what's this memory for? Why do I need this memory? If I'm just saving my files to the to the hard drive, why do I need another kind of memory? Well, the CPU can't really keep a lot inside of it, like a lot of information inside of it. If the CPU is like working with an entire file, like a picture or something like that, it's processing a picture to try to draw it onto the screen or something like that, it needs to actually put that picture in some area of memory that it can access very quickly. Okay, so when I said that the CPU is like the brains of the computer, it's like the brains without the memory. Okay, so there's this other kind of memory which is basically a temporary memory that the CPU uses while the computer is running. Okay, as soon as the computer shuts off, this memory disappears. Okay, whatever's in that memory, the physical memory doesn't disappear, but whatever's in that memory dissipates away. Okay, this is why you don't want to shut down a computer by just like unplugging it or abruptly turning off the computer. You want to use the proper shutdown, and that's because a lot of the information when a computer is running is inside of the memory, and the computer, as it shuts down, it takes it from the memory and it puts it onto the storage unit. Okay, so that it's stored for the next time you reboot the computer. But you know that if you're in the middle of like typing a paper, okay, like in Microsoft Word. Now, Microsoft Word does have autosave every once in a while, okay? But if you turn off the autosave and you've been typing away at a paper for half an hour, that paper isn't on the storage, okay? It isn't on, on your hard drive. It's actually in the memory. And if someone comes by and they just unplug the computer abruptly, everything that you've been doing, because it was in the memory, it just disappears and you lost all that information. Now, there's a lot of safeguards against a computer, that happening to a computer. But, yeah, it can happen. Like you can have just like an abrupt power outage, and whatever, you were working on just recently, since the last, autosave that Microsoft Word did, that was in RAM. That was in this volatile memory. And volatile means that it, floats away. It goes away when the power goes off. And so, if there's a power outage, you lose all that information. Okay, so like to shut down a computer properly or a laptop properly, you have to go to the button, the icon, and go to shut down, and it'll shut it down. Okay, a lot of people, especially with laptops, you'll just close it and they go to sleep. Okay, that sleep still gives the RAM a little bit of memory. Puts a little bit of power onto the memory so that the memory isn't lost. Okay, so that's why it's sleep and it isn't actually off. All right, but if you actually power off the computer, whatever's in RAM is lost. Okay, and so you might say to yourself, well, okay, great. Now that I understand RAM, how much of it do I want, and why would I want more? Okay, well, generally speaking, you want at least 4 gigabytes. Okay, I say here very little. I would say little. I don't know if it's very little, but depends on what you're doing. Basically, think of it this way: it's the temporary memory that the CPU needs as it's doing its job. Okay, the more tasks you give your computer, okay, like the more windows you open up. If you've got a browser going, you've got like Microsoft Word, and maybe you're listening to music, and we've got a whole bunch of things going on in your computer at once. Each one of those tasks takes up some memory. So basically, the more memory you have, the more tasks your computer can do before it starts to slow down. Okay, so that's why you might want more memory. Later in this lecture, I'm going to talk about virtual machines. And virtual machines are like computers within computers. And so not only are there all the windows that you've got running, but if you're going to be running virtual machines like computers within computers, then you're actually going to need more RAM for all of those little virtual machines that are running inside your computer. Okay, so it depends on what you're doing, but for like ordinary use, 4 gigabytes I would say is a minimum. But if you're doing more than that, you're going to want maybe up to 64 gigabytes. Okay, and it's not that expensive these days. Okay, another reason you might need more RAM is if you're doing gaming or if you do a lot of video processing. And what I mean by that is like video editing. Okay, kind of like what I do with my videos before I put them up on YouTube. Okay, I need some RAM, otherwise it starts to slow down the machine significantly. Okay, so typical cost for RAM, 32 gigabytes. Okay, for $200. All right, so let's take a look at Tiger Direct here, and where's that? Oh, sorry. Well, actually, let me show you the RAM, and then I'll go back to that. This is some RAM here. So this is a 32 gigabyte kit of RAM, and it's basically, if you see this, you go, well, where does this plug into? It plugs inside the computer, inside the onto this thing called the motherboard, which I'll show you towards the end. But there you go, 32 gigabytes. This is kind of nice RAM, and it's only $200. Okay, and 32 gigabytes is more than enough. All right. By the way, I overlooked showing you this. This is actually back to the storage. This is an SSD. Okay, so just to remind you, I showed you this, and that was a SATA drive, which is a platter. Okay, and this is whoops, right here. That is an SSD drive, and you could see that this SSD drive is 2 terabytes in size. Okay, for about $300. Okay, and so it's a lot more expensive than the 6 terabyte drive for $200, but again, that's much faster. Okay, so depends what you want. All right, let's move on. What other components are there inside of a computer? Well, there's the graphics card, okay? And the card, the sky's the limits. The sky's the limit with graphics cards because you can buy a very cheap one that'll just do some rendering, onto the screen, just draw pictures on the screen or so on. And you can buy graphics cards which are like for high-end gaming, okay, especially first-person shooters, where you're moving around a lot and you want the rendering of the frames to the screen to be very, very fast, okay? So some graphics cards are even more expensive than computers. So here I just picked one. I wouldn't recommend getting, a graphics card that's this expensive, okay? But there's an example of an NVIDIA, that's the company, Quadra RTX 4000. They're selling right now for about $1,000. Okay, and again, this is really high end. The only people that would really want this is people that are either doing gaming, some high end gaming. Okay, and also some very specialized things such as hacking. Okay, cracking of passwords, and also Bitmine coining. Okay, let's not talk about that too much. I'll tell you a little bit about bit mining later on. But basically, there's some very specialized uses of graphics cards that have nothing to do with graphics. Okay, so there's more use to a graphics card than graphics. Okay, so let's take a look at a graphics card here. And here's the that card that I just mentioned, the NVIDIA Quadra, selling for a little over $1,000. Okay, and like that's more expensive than some laptops. So you wonder, why would anyone ever want that? Well, I just told you why. For these kind of specialized purposes or for high-end gaming. Okay, I should also warn about buying something which is too expensive because Moore's law applies not just to the entire computer, but it applies to everything. So if you buy a graphics card now for $1,000, in a year and a half, it'll only be worth $500. And so they depreciate in value pretty quickly. Okay. And then the last thing that a computer has, if you were to open it up and look inside, is this thing called the motherboard. It's what everything plugs into. Okay, so you've got that CPU and it plugs into something. You've got the RAM and it plugs into something, the memory, and you've got the hard drives, the storage, and that plugs into something. The graphics card plugs into something, and so that board. There's a flat board that everything plugs into. It's called the motherboard. Okay, so let's take a look at a motherboard here. So here's an example of a motherboard. They're not that expensive, and it's a little hard to see here, but like this image right there that you're looking at, you could see here how you can plug into various slots. Okay, so this central square right there, that's what the CPU plugs into. Okay, and then over to the side here, you see these two slots here. That's where the RAM plugs in, or the memory. Okay, and then there are these other slots here. One of these would be the graphics card. Okay, and also you don't see here, but there's a wire that goes from the hard drives to the motherboard, and I can't see where they get plugged in here, but there'll be a place where you can plug in hard drives here. Okay, the motherboard, because if you take a look at the very back of the computer, you know how there's like this place where you can plug in your USB drives, and where you can plug in your mouse and keyboard, and where you can plug in any like speakers and things like that. All of those are being plugged into the motherboard. Okay, and that's the only part of the motherboard that's exposed outside of the computer. Okay, so that's everything that you would have inside the computer. And the only other thing that I would mention at this point are what are known as the peripherals. And there again, the sky's the limit, because there's a lot of different things that you can plug into a computer. Like the mouse, keyboard are considered peripherals. The monitor is a peripheral. Anything that's outside the computer itself or the laptop itself, okay, is called a peripheral. Scanners are peripherals. Computers run large equipment, so like an x-ray machine could be considered the peripheral of the computer, and so on. Okay, and so since computers run everything, like a smart TV, okay, so the computer's inside the peripheral of the smart TV, but the smart TV itself, the TV itself is actually the peripheral of the computer. Okay, so I hope that gives you a little bit of an idea of what is inside a computer. This is kind of the gross anatomy of a computer. Let me just quickly summarize it because there was a lot of information there. Okay, and so let's just go over it very, very quickly again. Uh, there's the CPU, that's the brains of the computer. Okay, CPUs belong to various families. There's like the 64 and 32-bit Intels, and then there's the 64 and 32-bit ARM. Okay, the Intels are inside of laptops, desktops. The ARMs are inside of phones and tablets. Okay, then there is the storage unit. That's basically, like the hard drive where the information gets stored. Okay, the bigger the hard drive, the more files you can store before it gets filled up. Files like movies, pictures, homework, whatever. Okay, there is the RAM, also known as the memory. Okay, and the more memory you have, the more tasks the computer can do at the same time, simultaneously or in parallel. All right, and there is the graphics card, and that's what's responsible for drawing the picture on the monitor. All right, and then there's the motherboard that everything plugs into. Even your phone has a motherboard. If you were to open up your phone, don't recommend you do that, but if you open up your phone, you would see that inside the phone there's basically a board, and everything is plugged into that board. And finally, there's everything else that's outside that plugs into the computer from the outside, and those are known as the peripherals. Okay, that's enough about the hardware. Okay, so let's now turn to the software. Okay, the software is basically the instructions that you give a computer. So a computer is different than any other machine we've made. If you think about the mechanical muscles, to use the language of CGP Grey, machines that just do mechanical things, like a crane that lifts stuff. Okay, or even a car. What does a car do? It just moves from one place to another. There's not a heck of a lot of instructions that you give a car. You turn the key, that turns it on. Okay, you turn your wheel, and that turns your steering wheel, and that turns your wheels left and right. Okay, you step on the gas, and that goes forward. You're kind of telling the car what to do in real time. The same thing with a crane and stuff like that. Okay, but with a computer, it's actually much more versatile. All right, the software are the set of instructions that you give to the computer so that it can do a task. All right. Now, there's that operating system, and we'll get into that, but let's just think of the apps on your phone. When you buy your phone, there's a few apps that come with it, like, the app to make phone calls, because after all, it is a phone, okay? There's usually a calculator in there, and there's usually a browser, okay, so that you can surf the internet. And those are all apps that come with the phone. But, you might say, I want to play a game. I don't know, I want to play Candy Crush. Okay, and so the phone, when you buy it, it doesn't have Candy Crush installed, and so you say, well, I want to play this game, and you just download this file, and this file is actually software, and it's instructions, and it teaches your phone how to play Candy Crush, and then you play Candy Crush, and then you go, well, now I'm bored of this, okay, and you say, I want to play something else, and you can download that game. Okay, and you say, well, you know what, I actually need something for work. Okay, and you download that app. Okay, and you got the idea. You can just keep adding information to the computer in the form of software, and that just teaches the computer to do more. And then you can also have the computer forget stuff, because you go, you know what, I got to take Candy Crush off the phone because I'm getting addicted to this game, and then you can delete that. Okay, and so computers are they're a little bit like humans. You can teach them things, and then well, I guess it's not good to unteach humans things, but you can take information out of computers. Okay, so software is like what you can add and remove, and to a computer to expand its functionality. And this is far beyond anything that you could do with simple mechanical muscles. Okay. I don't know, like a tractor that's used, but that a farmer uses to till up the soil. Again, what kind of instructions do you give it? You start it up, you start it going. Maybe there's an up and down button for, like, the thing that digs into the ground, the component of the tractor that digs into the ground and starts tilling the soil. Those kinds of things. There's just some simple instructions, but you're not really teaching this thing. You're just kind of giving it the instructions at the time that you want it to do it, okay, in real time. Okay, so computers are on a whole new level, and the software is that set of instructions that you can give the computer that teaches it how to do these extra tasks, okay? It's called soft in contradistinction to hardware, because remember, the hardware, you can't really change the circuitry in there. You can't go into the CPU and say, I'm going to teach you how to do some new kind of arithmetic by rewiring the transistors. They're hard coded into that silicon wafer, and that's not changing. But what you can do is you can change the software very easily. So the way I like to think of hardware and software is the hardware is the unchangeable or the hard to change parts of the computer, and the software is the easy to change parts of the computer. Okay? So what is this software like? Okay, well, it's usually like on a phone, it's usually an app. Okay, it comes so the software comes bundled in apps, or on a desktop, it comes bundled in the form of programs. And just like you would download a picture from the internet, you can download an app from, say, the Google Play Store, from the Apple Store, or whatever. And they're just a file. And when you first download them, they're just a file like any other file. So it's like downloading an image or downloading a movie or whatever. Okay, and then when you click on it or tap it on the phone, it starts up. And that's different than a picture. I know a picture will just appear on the screen, but a picture is in the set of instructions that teaches the computer what to do. A picture is just something to be rendered onto the screen, whereas the software is actually these instructions that are executed on the computer. Okay, typical sizes of apps would be like a small app for, say, a calculator. I looked on my phone earlier, and a small like a calculator was the smallest app I had at about 10 megabytes. Okay. And larger apps are like about 200 megabytes for, say, something like Chrome on my phone. Okay, and remember, your phones are like earlier I showed you that Samsung, which was I think 64 gigabytes. Okay, and a large portion of that is actually taken up by the operating system. My phone, it's an older phone, only has 8 gigabytes. Okay, and so you can imagine that if one app is like 200 megabytes. Well, if you have 5 of those, okay, 5 apps at 200 megabytes, that's 1,000 megabytes. 1,000 megabytes is a gigabyte. I've already used up an eighth of my phone with just 5 apps. Okay, and so yeah, it's easy to fill up a phone. Okay, at 64 gigabytes, it gets a little harder, but if you've got some movies on there, and then you try to start putting apps on top of that, you can fill it up pretty quick. Okay, so those are the sizes of typical apps. Okay, and again, they download and they'll sit there dormant on your in the storage of the machine, and they're taking up space in the storage, but they're not doing anything until you tap them, and then the CPU goes, oh, you want me to do the instructions here, and it starts to read the app, and it goes, okay, you want me to do this, you want me to do that, you want me to do that, and by executing all those instructions, the app does whatever it's supposed to do, like, I don't know, play Candy Crush, of course. Okay. All right. The apps, though, I've been concentrating on the apps because that's what most people are familiar with. You're familiar with the programs that you run, like Microsoft Word, and you're familiar with the apps. But there's another part of this the software which is much more important than the apps, although you can't see it. Okay, it runs in the background, and this is what's known as the operating system. Okay. And the operating system is different than an app, because with an app, like I said, it stays dormant on the storage until you tap it, and then it comes alive and it does its job, and then you can shut it down. Okay, the operating system, it's not like you can turn it off or turn it on. Okay, like an app. All right, as soon as you turn on your phone or your computer says, I need an operating system. It finds the operating system, and it loads it into memory. Okay, so the operating system gets loaded into memory when the computer starts running, and it's running all the time, okay, in memory during the entire uptime of the computer. As long as the computer is running, like the power is on, that operating system is in the background doing its thing. And the only time the operating system disappears or is shut off is when you shut off the computer. Okay, so that's the big difference between the operating system and the apps. The operating system is resident in memory during the entire uptime of the computer. When I say uptime, I mean during all the time when it's powered on. Okay, whereas the apps, the user says, oh, I want to turn on an app, I want to turn it off, I want to turn on another app, I want to turn it off, and so on. Okay, and this operating system is in the background, and it's doing its thing in the background. Okay, so why do we have like two layers to this software? Like what happened here? Like why don't we just build these things so that they're just apps running directly on top of the hardware? And the reason is that since about the 60s, software started to divide into two layers. Okay, so remember, software is the instructions to the computer, but there's like two layers of the software. There's this operating system which runs in the background, okay, and it does some very specialized tasks. And then there's the apps which you as the user decide to turn on and turn off. Okay, the reason it evolved that way is because over time there turned out to be more and more specialized tasks that needed to be done by one program that was always available. Okay, yeah, you could think of it as kind of like the manager that manages all the hardware and all the apps. Okay, so it's like the central manager of the entire computer, and that's the operating system. Okay, to understand the relationship between the user, the apps, the operating system, and the hardware, there's this picture. I didn't make this picture up, it's all over the internet. There's this picture right here. Okay, and basically it shows the human-computer interaction in 4 layers. All right, so the uppermost layer, this is you. Okay, so you interact with a computer, your phone. Okay, and you say, well, how do you interact with it? All right, well, from the hardware point of view, maybe you're moving your mouse around or maybe you're touching a screen. But think of it from the software point of view. You're like tapping on an app. Okay, so you're interacting with the apps, you're interacting with the programs. So you as the user, you don't actually see that operating system because it's in the background. You only interact with the apps. Okay, and the apps interact with you because what the apps do is they'll like draw a picture onto the screen and they'll say, hey, like if it's a calculator, you'll do 3 plus 4, and when you press the 3, it draws a 3, and when you press the plus, it might put a plus up there, and then when you press the 4, it draws a 4, and then when you hit the equals, it puts the number 7 up there. Okay, and so you're interacting with the app by tapping on the screen, and the app is interacting back with you by drawing things on the screen. Okay, so you interact with the apps and the apps interact with you. Okay, you do not interact directly with the operating system. If you're going to do anything with the operating system, it has to be through an app. Okay, the apps in turn, they communicate with you, just talked about that, but they also communicate with the operating system. So if the app needs to do something with the hardware, it cannot communicate with the hardware directly, which is the lowest level here. The app has to actually ask the operating system to do something, and then the operating system can ask the hardware to do it. Okay, so the apps are separated from the hardware by this extra software layer known as the operating system. Okay, these two layers together, okay, whoops, these two layers together, the programs, the apps, and the operating system, they're both software layers. Okay, but the operating system is what's known as low-level software. It's in the background. Okay, and the apps are higher level software. They interact with the user. Okay, each layer in this picture can only interact with the layer directly above or directly below. It can't skip a layer. Okay, so the apps can't directly interact with the hardware. All right, they have to go through the operating system to do that. And you say, well, why did we design it this way? Well, it wasn't this way all the time, but starting around the 60s, there started to be a bifurcation between programs which were purely for the user, okay, called programs, and now we call them apps, applications, okay, and operating systems which were responsible for properly orchestrating everything in the computer. Okay, and there was an advantage to this. Okay, the advantage to this was that the operating system could properly take control of the machine and make sure that things worked well. Okay, so the operating system gave the user, I shouldn't say gave the user, but it made the entire operations of the computer much better than if just the apps were directly interacting with the hardware. Okay, so what are the kinds of things that the operating system does that makes the whole computer experience better? Okay, I don't want to say computer because I'm not talking about the physical hardware. What I'm talking about is the entire functioning of the computer. Okay, so the operating system, the existence of that operating system layer makes the entire functioning of the computer better. Why? Well, it makes it more efficient. Okay, and the reason is makes it more efficient is because the apps, they don't necessarily know about other apps that are running on your phone. Okay, and one app could just decide to use up all of the CPU time. And so this one application saying, you know what, I'm going to use 100% of the CPU time for the next 5 minutes, in which case your phone can only run that one app. Okay, and the other apps, they're kind of locked out. Okay, they might be there, but they don't have any time on the CPU. And if they don't have any time on the CPU, they can't do any computations and nothing happens. Okay, so in order to prevent any app from monopolizing the resources of the computer, the operating system says, no, it's your turn now, it's your turn, it's your turn. And so basically the operating system makes sure that the resources, the hardware resources, are used fairly by all the apps on the machine. Okay, and this is what's known as efficiency. Okay, so that everything kind of runs efficiently. Okay, that's one thing that the operating system does. All right, and so in answer to the question, why did we design it that way? Because if we didn't have this operating system, how would you make sure that the apps were fair with one another? Okay, it's like the manager is going to make sure that everything is being partitioned out properly. Okay, the other thing that the operating system does is it makes sure that things are secure. Okay, so the apps, they can't make use of the hardware unless they ask the operating system. So apps can't just look anywhere on the hard drive. Okay, because that storage unit, the hard drive, it's got information on it, and some app might want to look at some information from another app and circumvent questions and things about privacy and so on. And the operating system is going to say, no, you don't have permission to do that. So on an Android, when you go to install an app, it tells you sometimes this app wants to access your pictures, or this app wants to access your contact list and stuff like that. And you can say no. And if you say no, what you're basically telling the operating system is this app does not get to look at my contact list. Okay, it cannot look at that. So if the app said, I want to look at the contact list, it can't do that directly. It can't directly look on the storage unit and find the contact list and read it. It has to say to the operating system, so the app says to the operating system, can I please look at the contact list? Well, if you've told the operating system, no, don't let this app do that, the operating system is going to say, nope, I'm not going to let you do that. Okay, and so by the operating system allowing certain things to happen and not allowing other things to happen, it gives you security. Okay, so that's another thing that the operating system gives you. Okay, the third thing that the operating system gives you, and this is a little harder to understand because today computers don't crash quite as much as they used to. Okay, they still do. But by crash, I don't mean just like a program closing down. I mean the entire computer just locks up and freezes. Okay, now a computer could do that if it has a hardware problem. But in the old days, okay, say 20 years ago, it was not uncommon for a computer to have no hardware problem with it at all. So the computer was perfectly fine. But the operating system was not that good, and it would lock up the hardware. And by lock up the hardware, I mean something bad would happen in the hardware where it kind of gets stuck in a loop or something like that. And the computer's just stuck doing this one thing and it can't get past that. Okay, the hardware is stuck doing something, and the entire computer would just, like, you couldn't move the mouse around. Okay, the entire computer would be frozen. Okay, and you would say, well, now what do I do? Well, there was nothing to do. You'd have to shut it off and reboot it. And if you were in the middle of working on something, you lost that, and there was nothing you could do. Okay, now those were older operating systems, and over time, operating systems have been getting better and better and better and better. Okay, so they started in the 60s, and they were very primitive in the 60s. Okay, by the 70s and the 80s, they were okay, kind of like for specialized things, they were okay, but generally they weren't that good. By the time you got into the mid 90s, like Windows 95, that was all right, but Windows 95 used to lock up quite a bit. Okay, and then through the 2000 and 2010, they really improved. All right, and now with like Windows 10, it's pretty good. Okay, and the other ones, which I'll talk about in a minute. Okay, I'll go through all of the major operating systems in a minute. This is what's known as robustness. Okay, so the uh, the operating system makes sure that none of the hardware gets into a state which locks up the computer. Okay, so that could happen. Hardware can get into a really bad state, in which case, get the CPU is always stuck on that particular piece of hardware, and it's not going to do it's not going to be able to function past that point. And modern operating systems are meant to prevent that kind of thing from happening. My old phone froze a couple of times that I remember. Like, I was literally using it and it just like froze and I couldn't do anything. I had to shut it off. And then once I couldn't even shut it off by the button, I actually had to remove the battery. So I had to open it up, remove the battery, leave the battery out for a few minutes, and then put the battery back, and it came back up. My newer phone, which I've had now for about a year and a half, never did that. Not once. I've never seen it freeze. Okay, and that's because the operating system is Android is just getting better and better and better all the time. Okay, and then the last thing, and this is a not something that you would necessarily know about, but different hardware has different requirements. And so if the apps had to know about all the different types of hardware that's out there, it would be too much for apps to know all that. So the hardware, this operating system, what it does is it presents the hardware to the apps in this kind of a unified fashion. Okay, that frees the apps from having to worry about any kind of idiosyncratic details about hardware. Okay, so one particular monitor might work one way, and a different monitor might work a different way. And if the apps had to know like every different type of monitor that was out there, it would make these apps huge because they would have to have all this different information. Okay, if I have this graphics card, if I have this monitor, then I do it this way. If I have this graphics card and I have that other monitor, I do it a different way. Imagine that an app had to have all that information for all the different types of monitors and all the different types of graphics cards. It would be too much. And so that information is taken care of by the operating system, and the operating system presents the graphics card to the apps in this kind of simplified fashion. Okay, and so that's yet another advantage of operating systems. That's why things were designed the way they were. Okay, so historically there were lots of different operating systems. Okay, but nowadays only a few of them are actually out on the market. And you say, well, what happened to the other ones? They kind of people just started using the better ones. And so the ones that weren't quite as good, they kind of went by the wayside, okay, over time. But once upon a time, there was a whole bunch of different operating systems, okay? But nowadays, there's not that many, all right? So if you're talking about a desktop or a laptop, you're looking at either Windows 10, okay, if you're in the Microsoft world, or you're looking at Mac OS X, okay, if you're in the Apple world. Okay, you can also run this other operating system known as Linux on either a PC or on a Mac. Okay, and it runs pretty good. All right, in my demo that I'm going to do after this lecture, okay, I'm going to show you how to install Ubuntu Linux in a virtual machine. But it's pretty good, and it does everything that Windows 10 will do, or everything that Mac OS X will do. All right, so you can install that on there. But a lot of people, I don't know, if they're used to the operating system that they've been using all the time, then they don't want to necessarily make a switch. Okay, but it is there. It is there, and Linux isn't actually an operating system. It's actually a family of operating systems. There are different flavors of Linux, okay? Like I just mentioned, Ubuntu Linux. So Ubuntu Linux is one particular flavor of Linux that you can install. I personally am a Gentoo developer. I work for within a Linux distribution known as Gentoo, and I develop that. And Gentoo Linux is just yet another type of Linux distribution which you can install. Okay, so it's actually a family. Okay, Android is actually very closely related to Linux. All right. The advantage to Linux is that it's free. Okay, so when you buy a computer that has Windows 10 on it, or a Mac, you can't. By the way, you can't buy a Mac without an operating system. Okay, when you buy a PC, it usually comes with Windows 10. Okay, or I shouldn't say usually, almost always. You have to go out of your way to buy a PC without an operating system on it. Okay, and the reason is you can't run the computer without an operating system, and you'll see that in my demo as well. Okay, so you can buy a computer without an operating system on it, and if you install Linux, Linux is free. You can just download it from the internet. You don't have to pay anything for it. With Windows, when you buy that computer, you're paying a little bit to Microsoft for Windows 10 to be on it. Okay, so maybe you bought a Dell, and the Dell is the physical thing, but the operating system running in it is Windows 10, and so the company Dell, gets most of the money, but some of the money that you paid for the computer goes to Windows 10 for the licensing. Okay. There's another advantage to Linux, which has to do with the fact that it's open source software, but I'll leave that to when we talk about open source. Okay, it basically has to do with confidence about what's inside the operating system. Okay, whereas Windows 10 is kind of secretive, Linux is open so that everyone knows what went into making Linux. Okay, but that's the world of computers, laptops, desktops, and so on. Tablets and phones, they tend to run either Android, okay, if you're in that world, or they run, like the iPhone will run an operating system known as Mac iOS. Okay, and that's the operating system on an iPhone. Okay, and that's basically it. Those are the major operating systems that are out there. There are others. Okay, and there's like OpenBSD. There's a whole BSD family, just like there's a Linux family. There's the BSD family, but generally speaking, unless you're like really off in geek land, okay, you've got some very specialized purpose, you're not going to be running one of the BSDs. Okay, you'll be running either Windows 10 or Mac. Okay, now there were advantages to making the operating system responsible for the hardware. Okay, I just mentioned what they were. But there is a disadvantage. Okay, so there was kind of a price that was paid, and it wasn't obvious as when operating systems first started to evolve, because people said, look, we just need a layer here to do that, to take care of this hardware, and it just kind of evolved that way. But the disadvantage is basically that the apps have to be targeted to that operating system. Okay, so there has to be a compatibility between the apps and the operating system. Well, think about it. What do the apps do? If the apps need the hardware to do something, they have to ask the operating system. So that means that the operating system and the apps have to speak the same language. You can't have an app that speaks Mac OS X work on Windows 10. Okay, and that's what we mean by this word targeted. Okay, so basically, if you're going to run a program, and say you download a program from the internet, you can't download a program from the internet that runs on Windows 10, download it onto your Mac, and expect it to run in a Mac. Okay, you can download it, you can put it on your desktop, you can double click the installer, but the computer will go, I have no idea what to do with this. Okay, and the reason is because the program, the app, and the operating system have to be compatible with one another. And because there were so many operating systems once upon a time, basically you might have an app which only ran in Windows. All right, and you go, but I don't have a Windows machine, I have a Mac machine. How do I get this Windows program to run on a Mac? Or the other way around, you had this Mac program and you wanted to run it on Windows. You go, how do I do that? Okay, so this became a problem, and it was a much worse problem in the past when there were more operating systems and more apps that were incompatible with the different operating systems. It's a little bit better today because there's fewer operating systems. Basically, you're down to, I would say, 2 operating systems on desktops, laptops, and 2 operating systems on phones. And that's it, okay, for the typical user. All right. Linux is pretty popular in Europe. It's not quite as popular in the US. But, if you add in Linux, then, you're just looking at 5 different operating systems. So the incompatibility isn't that bad, but it is there. Okay. An example of the incompatibility is Windows Access, which is a databasing program. Okay. And Windows Access only runs on Windows 10. It does not run on a Mac. So suppose you're working at a job and you have to use Windows Access, and you need to bring that home. But you say, well, I only have a Mac at home, or my laptop's only a Mac. You can't run Windows Access on it. Okay. Now they could make it run. Microsoft could make it to run on a Mac OS X, but they don't want to. Okay. And so you have this incompatibility in there. Okay. It depends on what the developer wants. So a developer, that is the people that actually make the software, that make the apps, okay? They might make the app so that it runs only on one operating system, or they can make the app so that it runs on different operating systems, okay? So a good example of this is like Firefox, all right? So Firefox has basically been developed for everything, for all operating systems, okay? There's Firefox for Windows, okay? And there's Firefox for Mac OS X, and then there's Firefox for Linux, and that's if you're in the laptop desktop world. But there's also, you know, Firefox for like Android, and Firefox for Mac iOS, which runs on the iPhone, and so on. And so, you know, because the Firefox developer said, we want this to run on every operating system out there, they made it so that it would run on every operating system out there. But if the developers don't do that, then that's not going to happen. Okay, you're not going to have like compatibility between every single application and every single operating system out there. Okay, let me show you where that, you know, where that occurs. So if we were to go to say the Firefox home page, well, download page here. Okay, so this is the Firefox download page, and you take a look at the kinds of options they give you here. You'll see that you know, there's Firefox, but there's various versions of Firefox. But, you know, basically if you pick Firefox here, it's going to ask you a few things. First of all, it's going to ask you what your operating system is, okay? And then over here, you can see that you've got 64-bit Linux, and that's what came up by default on my machine, because I'm actually running Ubuntu Linux. I'm on this desktop that I'm recording right now, okay? So usually when you go with a browser to a site, you're going to download something, the browser says, oh, by the way, I'm running on a machine that is a 64-bit Linux machine, and so the browser will default to that. But, you know, you could download something for like 64-bit Windows, okay? Or you could download for, okay, here we go, 32-bit Windows, okay? And you could download for Mac OS, okay? And by the way, Mac OS is only 64 bits, and you could download for 64-bit Linux, or you could download for 32-bit Linux, like that, okay? And so you get a choice, and you say, well, which one do you want? Well, if you're running Windows 10 at home, and for some reason, you know, the browser doesn't really tell the remote site what operating system you have to download the Windows 64-bit, okay? Otherwise, what you download, if you double click it, it will not install on Windows 10. All right, so for instance, right now, I'm not going to do this, but trust me, you know, if I were to download Windows 64-bit Firefox onto my Linux machine and I double clicked it, it would just do nothing. It would go, I have no idea how to open this file, okay? It wouldn't even know that it's a program, or an installer, actually, okay? And so that's this business of compatibility, and it's still with us today, okay? Like I said, it's not that bad. And a lot of software like Firefox says, okay, you know what, we're Firefox developers, we're going to develop for everything, okay? And so they make sure that it runs on every operating system, but that may not be the case. All right, so at this point you might say, well, is there a way around this compatibility issue? Okay, and there is, all right, there is a way around it. In other words, if you have a Mac at home, there is a way of running Windows on the Mac. You go, really? Yeah, there's two ways of doing it, okay? I'm going to show you one. In my demo, I'll actually demonstrate how you can do one, but there's another one which I won't demonstrate, okay? So there's two ways of actually running Windows programs on a Mac, okay? The first one is what's known as dual booting. All right, so I have to describe a little bit about how computers start up. When you first turn on a computer from off, the computer says, I got to find an operating system, okay? It can look for the operating system in a whole bunch of different places, okay? The first place that it usually looks is on the hard drive. And if it finds the operating system at the hard drive, it starts up the operating system there. It could start up the operating system off of a USB stick, okay? So usually, you know, you put like your homework, your pictures, maybe a movie or two on a USB stick, and you can watch them off of that, okay? But you can put an entire operating system on a USB stick, plug the USB stick into the computer, and then the computer can actually boot off of that. Now, suppose that there's an operating system on the hard drive, and you also put a USB stick in there with an operating system. Now, there's two operating systems on two different storage units. There's an operating system on the internal storage unit, the hard drive, and then there's an operating system on the USB drive, USB stick. And the computer says, well, which one do I want to start up? Well, there's a default, but if you want to switch between the default, you want to say to your computer, I know you usually start off with the hard drive, start up off of the hard drive, but for this one time, start up off of the USB stick. There's a series of keystrokes that you can do when you start up the computer to tell it to go to the USB stick rather than the hard drive. Okay, and usually on a PC, that's the delete key. Okay, I can't remember what it is on a Mac, but there's an equivalent on a Mac. Okay, and that's kind of neat because it means that you can actually start a computer off of this USB drive, and it looks like a totally different computer. Okay, because it's a different operating system, everything looks different. Okay, and then you can shut it off and then reboot it off of your internal drive. But you can actually take the internal drive and divide it into two pieces. Okay, you don't physically divide it, it's virtually divided into two pieces. This is called partitioning. And so now your one drive can actually act like two drives. Okay, physically it's one drive, but it acts like two independent drives. And you can install one operating system on one half of the drive, and you can install a different operating system on the second half. Okay, so once again, you've got your hard drive, you partition it into two pieces, and you might have Mac OS X on one partition, and you might put Windows 10 on the second partition. Okay, you can do this. All right. In a Mac, this is the program that does this for you is called Bootstrap. Okay, so I'm not going to show you Bootstrap because I don't recommend this. You'll see why in a minute. I'll show you a better way to do this. But if you want, just go to YouTube and just like, how do I use Bootstrap? And you'll get so many videos that'll show you this. And it's kind of cool because they'll also show you, if it's a good video, if it's complete, towards the end, they'll show you. They'll say, oh, press this key, and then you get to choose. Do I want to boot up in Mac OS X or do I want to boot up in Windows? Okay, and that's kind of cool. All right. And you could do the same thing with a PC. You could have it boot up in either Windows 10 or Linux. Okay, and I used to have a lot of machines which I would have as dual boots. Actually, this machine that I'm in front of, I forgot, is actually a dual boot machine. It can boot up either Windows 10 or it can boot up into Ubuntu Linux. Okay, so this is what's known as dual booting. And you might go, great. Why are you recommending that we don't use this method? Okay, there's two reasons. The first reason, it's kind of hard and tricky, and if you don't do it right, you can kind of mess up your machine, and then you got to bring it to the store and they can fix it for you. But that's kind of annoying if you have to do that. Okay, so that's one disadvantage. The other disadvantage is that it's like literally two computers. It's like a computer literally split in half. If you boot into Mac and you do Mac things, okay, so you're using Mac OS X on your Apple laptop, you're doing that, and you save a file, and you go, oh, now I need to boot into Windows. When you boot into Windows, you don't have access to the Mac file. So whatever you do in Mac stays in the Mac world, and whatever you do in Windows stays in the Windows world, and never do the two meet. So if you have a file in Windows and you want to get it into the Mac side, okay, like you got a movie, and you downloaded the movie while you were running Windows 10, and then now you're running Mac OS X, and you go, I want to watch that movie. You can't. You got to reboot the machine into Windows 10. Every time you want to switch between Mac OS X and Windows 10, you got to reboot the machine, okay? And then when you're in Windows, you don't have access to the Mac files. And then when you're in Mac, you don't have access to the Windows files, okay? It's literally like you split the computer in half, okay? So that's a disadvantage, all right? There is one advantage which I should mention, and we'll talk about virtualization in just a minute. When an operating system is running natively on the computer, that is normally the way it does. Natively means directly on the hardware without a virtualization layer between it, which I'll show you in a second. It runs better, okay? So let me say that again. When you boot a computer, the first operating system that loads, that's the native operating system. When the native operating system is running on the hardware, it runs most efficiently, okay? If you boot into one operating system and then later you do this virtualization trick to have a second operating system running, okay, in a virtualized environment, that virtualized environment is much slower, okay? So the advantage is that you get all that efficiency that I talked about earlier, okay, from both of the operating systems. So whether you're in Mac, it runs well, or you're in Windows, it runs well, okay? So it doesn't matter which one you boot into, it'll run very efficiently, okay? So that's the only advantage over the next method that I'm going to mention, okay? So there you go. there's dual booting. The other method, which is the method that I'm going to show you in my demo that I'll do after the lecture, okay, is what's known as virtualization. Now, virtualization is a little more involved in terms of like getting your head around what's going on. Okay, so computer has this hardware, but the hardware itself can be emulated within a program. Okay, so imagine an app which pretends like it's computer hardware. All right, let me say that again. Imagine a program, okay, an application which pretends that it is an entire computer. All right, so basically when you start up this app, it actually starts running, and it starts running as if it were a computer inside a window inside your computer. Okay, so it's like you can have a computer within a computer, and this is what's known as a virtualized environment. Okay, and actually in my demo I'm going to show you two virtualized environments. I'm going to show you how to run a computer within a computer, or a laptop within a laptop. Okay, but I'm also going to show you how to run Android within a desktop, okay, or a laptop. All right, and that one's a little bit more interesting. That's known as BlueStacks, and that's a little bit more interesting. And the reason that's more interesting is that, usually if you want to run an app, an Android app, you need a phone, right? And you go, you know what? I really would love to play Candy Crush on my laptop. Okay, I don't know if Candy Crush is available for the laptop or not, but imagine that there's an app, and this app only runs in Android. Why? Because the developers only made it for Android. They did not make it for Windows. And you go, but I really don't want to have to play this on my phone. I want to play this game on my computer. Well, then you run a program in your computer that pretends to be an Android phone. All right. So imagine a window, and this window looks like an Android phone. Okay. And then inside of the Android phone, inside of the virtual Android phone, you can actually install the apps and then run the apps in there. Okay. So you have the native hardware running the native operating system, and then the native operating system can support applications. One of the applications that it can support is an application which pretends to be an Android phone. And then inside of that application, there's the Android operating system installed. And then inside of the Android operating system, you can install the apps and then play the apps. Okay. And so you have these multiple layers. And at this point, it's kind of a little bit confusing. So what I did was I gave you another picture. Okay. So this picture is basically the same picture as above. All right, but I expanded it a little bit. All right, so above we have the hardware here, and I called it host, the host hardware. Okay, above I just called it hardware. That's because it's the hardware that is the real hardware. Okay, it's the real hardware that you can touch. Okay, like your laptop itself. Okay, now the hardware itself needs an operating system to run, and so there's the host operating system, also known as the native operating system, okay, to distinguish it from the guest operating systems, which I'll talk about in a second. And now that operating system, the native operating system, can support an app, it can support another app, it can support another app. Okay, like what are these apps? Okay, also programs. It could be like Firefox. Okay, so we're like, maybe this is Windows 10. Okay, and here's Firefox running, and here's Microsoft Word, and I don't know what else you might have running, maybe some game. Okay, and those are all Windows games, so Windows programs, sorry, these are all Windows programs running on Windows. Okay, and you say, but now I want to run an Android app. Well, these apps here can't be Android apps, because that app there has to run on that operating system. So if this operating system is Windows 10, then that app has to be a Windows 10 app. Okay, but here's what you can do. You can run a special app, a specialized app. This entire square right here, okay, it's hard for me to highlight it, but so this and that and that, okay, that whole box there, okay, let me just highlight, watch my cursor there, that entire box that I'm highlighting there with my cursor. Okay, that entire box, you think of it as one app. That app is the emulator. So what's going on inside this emulator app? It is pretending to be hardware. Okay, it is pretending to be like it's emulating real hardware. Okay, so even though you're on a computer that's running Windows 10, this emulator might be emulating an Android phone. That's what I mean by the guest hardware. The guest hardware is the virtualized hardware that's running inside of your real physical computer. Okay, so let's pretend that that guest hardware is, say, Android. And of course, or sorry, it's a phone. And the phone needs Android operating system. So the operating system there is Android. And now that operating system can sustain apps, and that might be an Android app there running on the Android operating system there, like that. Okay? So I know it's a little bit confusing, which is why I have the demo. The demo will really help. Okay? But basically, if you wanted to do this on your Windows 10, it's not that hard. You go to, you'll see it in the demo, but let me just mention what you do. You go to a site where you get the emulator. Say you want BlueStacks.com. You go to BlueStacks.com, download it, install it. Great. You start it up, and what it does is it actually looks like a window, but inside of the window is like a phone. It's imagine your phone, but as a window on your computer. Okay, and then inside of that window, you can go ahead and go to the Google Play Store and download Candy Crush, install Candy Crush, and then start playing it. Okay. In my demo, I'll do Clouds and Sheep. It's another game. It's a fun game to play. Something that I'll install quickly. All right. So that's kind of amazing. And so that's like an Android phone on Windows 10. But you can also do like a computer within a computer, and for that I'll do VirtualBox. Okay, and so you could have say you have to run a Linux program. Okay, and there are some programs out there that companies use that only run in Linux. Okay, and you say, but I have a Windows machine at home, or I have a Mac at home. Okay, so let's take the let's suppose that this time you have like an Apple laptop. Okay, so you have a Mac laptop. Okay, and of course the Mac laptop is running Mac OS X. All right, but now you need Linux. Okay, maybe you need Ubuntu Linux to run your program for work. If you try to install that program on your Apple laptop right there, it wouldn't install. Okay, so like I'm trying to run my Linux app here directly on Mac OS X, it won't run. Okay, what you can do is install an emulator called VirtualBox. Okay, so once again, like imagine that this entire, let me try to see if I can highlight, whoops, this, and no, I can't do it. But just imagine that, plus that, plus that. Okay, so those three lines there. So again, that entire box right there is a program. It's called VirtualBox. VirtualBox emulates an entire computer within a computer. Then you say, now I'm going to install Linux. But you don't install Linux on your computer, which is running Mac. You install Linux inside of VirtualBox. Okay? And so now you have here your virtualized computer, and now you've got Linux inside of there, say Ubuntu Linux, and then you can run that program from work that only runs in Linux inside of there. Okay? And this is what's known as virtualization. All right. So to get a better idea of what this is, you're going to have to watch the demo after this lecture. Okay, so what are the advantages and disadvantages to this system? Well, there's the disadvantage, which I mentioned earlier. Okay, with native operating systems or host operating systems. Okay, native means it's the operating system that actually loads into the computer as soon as you turn it on. You turn it on, the first operating system that loads is the native operating system. Okay, that's going to run efficiently. Okay, if you put this extra virtualization layer in there and then you run an app on top of the operating system, which the guest operating system, which is in the virtualized environment, which then in turn runs on top of the native operating system, you've got more layers in there, it's more inefficient. Okay, so back to this picture down here, these apps here, which are running on top of the native operating system here, on top of the hardware, these apps are going to run much more efficiently than these apps here. That app runs on top of a guest operating system, which runs on top of a guest hardware, which then in turn runs on top of the host operating system and the host hardware. Okay, so the more layers there are there, the more the slower it's going to run. Okay, you got to think about it this way: how does this app actually get the hardware to do anything. So here's the real hardware, okay? All right, that's the real hardware. Host hardware, native hardware, real hardware, they mean the same thing, okay? In fact, right here, I can even put the word or native, okay? Or real, okay? All those words are kind of synonymous, meaning not virtualized, okay? Whoops. All right. So how does this app actually get that hardware to do that? Okay, this app has to first ask the guest operating system, which then has to speak to the guest operating. Sorry, this app speaks with the guest operating system, which then speaks to the guest hardware, which then speaks with the host operating system, which then speaks with the host hardware. Okay, so there's a lot of layers of translation in there. So you can imagine that this app is going to run much more efficiently than those apps, because this app here speaks to the native operating system, which speaks to the native hardware, and less layers. Less layers, the more efficient it is. There's your disadvantage. Okay. So what's the advantage? The advantage is that it's kind of no hassle. Okay, you can install an operating system, a guest operating system inside of this virtual machine, and you don't really have to. You're not really messing with the low-level stuff of your computer. Okay, and so you don't have to do any of this dual booting. You don't have to do any kind of like stuff that might mess up your computer. It's pretty safe. Okay, and not only that, but you can only have one native operating system running, like I said, because it's the operating system that loads when you turn on the computer, but you can have multiple guest operating systems running. Okay, now each guest will take up some RAM, so the more guests you want to run, the more RAM you're going to need, and it can get pretty slow if you're trying to run too many of these. But suppose you have 64 gigabytes of RAM on your computer, and some computers are getting up there right now, and you give each one of the guests 4, well then you could probably run 3 or 4 of these guests no problem at all. Okay, and so that's kind of cool, because you can have, like on a Mac laptop, all right, you can have one window which is running Linux operating system, another one which is running Windows 10. You can have maybe 2 running Windows 10. Again, the limit is just how much RAM you have. All right, and so one of the reasons why you might want more memory, more than just the minimum 4 gigabytes, is if you're going to run these virtual machines. All right, and so there you go. This is known as emulation. And so this is the preferred method to get past the compatibility issue. Okay, so there was a lot of information there. Before I move on to the next topic, let me just sort of summarize what I've taught you with operating systems. Okay, so the first thing is that things evolved into, here we go, things evolved into 2 layers for your software. The low layer, which is the operating system, and then the apps. Okay, the operating system is the thing that loads when you start up your computer, and it's resident in memory all during the uptime of the computer. The apps are the programs that you start and shut off. Okay, you only interact with the apps. The apps interact with the operating system. The operating system interacts with the hardware. Okay, things evolve this way because the operating system has a very special task. Its task is to make sure that everything runs right. Okay, if all you had were apps, the computer would become a mess, because the apps would start to compete with one another, and there'd be like no referee that would keep the apps from interfering with one another. Okay, so the reason computer design software was designed this way is because the operating system ensures that your computer is going to be efficient. Okay, in other words, it's going to run smoothly and fast. Okay, it's going to be secure, meaning that the apps are not going to be able to get at information that they're not allowed to get at. It's going to make sure that it's robust, meaning that the computer doesn't just crash on you all the time. Okay, like things are going to run. I've had computers, I think the longest I've had a server run is 3 years. I'm not kidding. This is a server that from the time I turned it off until the moment I had to shut it down, it was over 3 years. Okay, now these are servers, and they were on battery backups. Okay, so even if the power went off, the batteries kicked in, and so this thing ran nonstop for 3 years. You say, well, wow, that's kind of impressive. Why was it able to run that long without it crashing or something going wrong? Because the operating system was robust. Okay, and then finally, and this one's a little harder to see, but the operating system makes the apps smaller, because then the apps don't have to worry about all the different types of hardware that's out there. Okay, the operating system does all the concern about like how to deal with all the idiosyncratic details about the hardware. Okay, so like, this hardware works this way, that one works that way, that one works that way. The operating system says, let me take care of the detail of the hardware. Apps, you just say to me, I want to draw this thing, and I'll draw it for you. Okay, and so that makes the apps a lot smaller, because they don't have to worry about all those details about how the hardware works. Okay, so that's why historically operating systems evolved that way. There's this compatibility problem between the the apps and the operating system. So an app has to match the operating system. We say in the business that this application has been targeted for a particular operating system. Okay, so you can't run Firefox for Windows on a Mac OS X, or you can't run Firefox for Linux on Windows 10. That doesn't work. Okay, you have to run Firefox for Windows on Windows. Okay, or Firefox for a Mac on a Mac, and so on. Okay, now most applications will run on all different platforms, because the developers did that, but sometimes you get an application that'll only run on one particular platform, one particular operating system, I should say. And how do you deal with that? Well, one way is the dual boot, which I don't recommend, but the other way is by running an emulator. Okay, and the emulator will emulate inside of your computer the operating system for the app that you want to run. Okay, so again, in the demo, you want to run an Android app in Windows 10. What do? BlueStacks does the emulation of the layer in between. So basically, you've got an Android app running inside of Android operating system, running inside of BlueStacks, and BlueStacks runs inside of Windows 10. Okay, I know that it's conceptually a little bit difficult, but it isn't that bad. Watch the demos, and you'll see what how that works. Okay, now next topic, last topic here. Operating systems, they do a lot of things, and I don't want to get into the details of what they do, but there's one thing that you really want to get into the details, and that is encryption. Okay, operating systems provide encryptions for hard drives or USB drives. Okay, basically any storage unit. Now, why is this important? So if you were to lose your laptop, you're in a sense losing three different things. Okay, first, you're losing the physical laptop. All right, and that kind of sucks. Maybe you paid like, I don't know, $700 for this laptop. Well, you're out that $700. Okay, lost. Unless you get it back, you've lost that. But you've lost more than that. Okay, what have you lost? Well, all those pictures you have that you don't have anywhere else. You didn't back them up anywhere else. So you lost, all those pictures. They were on that laptop. You didn't put them anywhere else, and they're lost too. So you lose the data that's on that laptop. Okay, sometimes the data is worse than losing the laptop. You say, you know what, I wish I had the data back, but I could always buy another laptop. Okay, but you lose one other thing, and that is possibly your information to a hacker. In other words, your identity. Okay, we could call it identity theft, but it might be more than even identity theft, because if someone gets your data, you know how your browser has passwords in it that allow you to get into your banking? Well, that kind of sucks, doesn't it? Because now the person who has that can get into your banking. Okay, and you say, well, just change the password on your banking. Yeah, well, change the password on like 100 different websites that you go to, right? So it's kind of hard. Okay, and you say, well, how do I protect against this third thing? And the answer is encryption. Okay, so what is encryption? Before I actually show you how to encrypt things, what does encryption even mean? Well, encryption is a mathematical formula called an algorithm. It's a mathematical algorithm that converts data that is useful to you, that you can read, that's humanly readable, into data that's not. Okay, so imagine that you have like some file. It could be even an ASCII file, but it could be anything, picture or whatever. Okay, and so suppose you have like just to make this conceptually easy, imagine you have a Word a WordPad document, okay, or a text document, and those are ASCII files, and in there you put all your information, like like your passwords, okay, and when you save that file to the hard drive, people can look at that file and they can see your passwords. Okay, so whenever the data is readable by a human being, we call that data plain text in this business. So plain text just means data which is directly readable by humans. Okay, well, even by a program, but it's directly useful. All right, to whatever purpose you have. Okay, so again, like you just double click on this file that has all your passwords, and the file opens up, and you can see all the passwords. Okay, now if you were to encrypt that file, what that means is that you would pass that file through this algorithm, this mathematical formula, which would scramble the file in such a way that it's no longer readable. Okay, now you have to provide a password. So it takes the plain text, this algorithm takes the plain text, and it takes the password, and it uses the password and the plain text together to do the scrambling, such that you get what is known as ciphertext. Now, if someone were to look at the ciphertext without decrypting it, they wouldn't be able to make any sense of it. So again, that file that has all your passwords, if they got the ciphertext, they try to open it up and look at it, it would look like gibberish. Okay, it would just look like garbage to them. They would not be able to see your passwords that are inside of that encrypted file. Okay, now I've been using the example of like a plain text file that contains plain text, like like a notepad file. Okay, but it could be anything. It could be a picture. You've got a picture in plain text, and you could just double click on it, and it appears and it comes up on the screen. If you were to encrypt it, that picture would now be ciphertext, and if you try to double click it and render it to the screen, it would look like gibberish. Okay, it would just look like garbage. And you say, but how do I get the ciphertext back into plain text? You run the algorithm backwards, but to do that, you need that password again. Okay, so to go from the plain text, which is readable, to the ciphertext, you give it a password. Okay, and then the algorithm scrambles everything up, and now you've got that ciphertext. And to go from the ciphertext back to the plain text, you run the algorithm again, but this time you again have to give it the password. So what happens if someone gets the ciphertext but they don't have the password? They can't decrypt it. Okay, all right, so you need this password, and it's the same password to encrypt the file and then to decrypt it. Okay, so it starts plain text, you encrypt it into ciphertext with a password, it's ciphertext, you decrypt it back to plain text with the same password. Okay, if the ciphertext gets lost or falls into the wrong hands, they can't do anything with it without that password. And where's the password? Well, hopefully it's in your brain, or if you want, like on a piece of paper, but stored somewhere far away from your computer or your USB drive or whatever. Okay, that's what encryption is all about. So in the scenario where you lose data, and it doesn't even have to be your whole laptop, it could just be a USB stick, and your USB stick has some very important information on it, social security number, passwords to banks and things like that. It's all on this USB stick, and you carry USB sticks all over the place. You lose it, someone gets that, if they're not a nice person, they won't try to return it to you. They'll just look at the data that's on there, and they'll have all your information. So now what? Well, now you've lost it. So what you can do is you can actually encrypt that USB stick. Okay, and now if you lose the encrypted USB stick, someone gets it, they can't read it unless they have your password. Okay, now you have the password, so you've got that USB stick, and when you plug it into your computer, if you try to access it, and I'll show you this in the demo. Okay, if you try to access that USB stick, it says I need a password to do that, and if you type in the password, then you can access it. If you type in the wrong password, you can't. Okay, this is encryption, and it's very important. Okay, especially today, because if you lose these things, then you lose the data. It could be really bad. All right. Okay, so this is the story behind how encryption works. I should warn you against what's known as a false sense of security. Don't think, especially on a laptop, that, like if your screen saves, how you have to enter in a password to get in, your login password. That's not enough, okay? The login password just locks you out of the screen. It doesn't actually lock someone out of the data that's on the hard drive, okay? What a good hacker could do is if they got your laptop, if I got your laptop, I would not turn it on. For lots of reasons, I wouldn't turn it on, okay? One reason is you don't know what happens when the laptop turns on. It might phone home. It might say, hey, I've been stolen, I wouldn't do that. What I would do is I would take a USB stick with my own operating system on it and plug it into your laptop. Okay, and then I would start it up, and I would do some special keystrokes that says don't boot off of the hard drive, but boot off of this external USB stick. Well, that's my operating system, and I now have total control. The data that's on the hard drive, that's sort of a sitting duck there, because now I've got my operating system, and the internal hard drive actually looks like an external drive as far as my operating system is concerned. And that login password and all that, that's not running. None of that stuff is running. I can just look directly on the data. Okay. Now, if the data is plain text, I've got it. I've got everything, all your information. But if it's ciphertext and I look at it and I go, oh no, this is ciphertext and I don't have the password, I'm locked out. Okay. So don't confuse the login password, which is just really a screensaver password. It just, in case you walk away from your computer, your screensaver locks, and then, people can't get in without typing that. Don't confuse that with good security. Good security means that the actual data right on the hard drive has to be encrypted. Okay, and operating systems will provide that for you, and they've made it pretty easy too. Okay, it's pretty easy to do that. So how do we do that? Okay, well, it depends on your operating system, obviously, because the operating system is responsible. Each one will do it in a slightly different way. Okay, so let me tell you how you do it on a Mac OS X. Okay, I'll tell you, I'm not going to demonstrate that for you in the demo video, but you can easily just Google or look up at YouTube for the following keywords. If you want to encrypt the entire laptop, okay, so now you're not just encrypting a USB stick, but the entire laptop, you use a program that's called File Vault. Okay, and basically you go to your system preferences, and inside your system preferences on a Mac, there's a thing that's called security, and then in security there's File Vault. Okay, even if you don't remember that, just Google for File Vault and it'll show you how to turn on File Vault. When you turn on File Vault, it basically takes a while, but it'll encrypt all of the information on your hard drive. Okay, then if you lose your laptop, no one is going to be able to see that encrypted data unless they have your password. Okay, now that's the entire laptop. You might say, well, you know what, I don't really care to encrypt my entire laptop, okay, or desktop. I just want to encrypt a USB stick. Okay, so you put the USB drive in, and then you use this program called Disk Utility. All right, there's a couple of ways of doing it, but Disk Utility is a nice way of doing it. Okay, and Disk Utility will say, well, what do you want to do with this USB stick? And you might say, encrypt it for me, and then it'll go through the procedure of encrypting it. Again, I'm not going to show you that demo. These are all pretty easy things to do, by the way. They're not at all hard. You could just go to YouTube and you can see how that's done. Okay. On a Windows machine, it doesn't matter whether you're encrypting the entire machine, which is the internal hard drive, or you're encrypting an external drive, which would be like a USB stick. Okay. Either way, you use a program called BitLocker. All right. And I will show you that demo. All right, so in the video that comes right after this one, there's a demo video. I do a demo of BlueStacks, VirtualBox, and the last demo will be a BitLocker, and I'll show you how to actually use BitLocker to encrypt a USB stick. Okay, so there you go. All right, now it's important that you understand the difference between encrypting and formatting. Okay, and the reason is that they're two totally different operations, but the reason is the same utilities that do the encryption oftentimes are related to the formatting. Okay, and formatting is a little bit dangerous, so you need to know about it. What formatting means is it means basically wiping the device clean. Okay, so if you've got a USB drive and you plug it in and you say format it, whatever files were on this USB drive, they all get wiped. They all get wiped. Okay, so do you want to do that? Well, sometimes you do. Sometimes you do want to format. And you say, look, I don't want to be bothered to drag everything to the trash and then empty the trash. You just wipe this thing and make it pristine. And that's what formatting does. Okay. So formatting and encryption, they're independent of one another. So you could, have files on there encrypted, and the files that were on there unencrypted now become encrypted files. Or you can format it, first and then encrypt it. Okay. But it's important to understand the two different operations because the same utilities will do both things, especially Disk Utility does that. Okay, and with BitLocker, it's two different tabs, but the two tabs are beside one another in Windows. Okay, so remember, formatting means wiping it clean, and encrypting means adding a password so you can't get at the files without that password. Okay, just one thing I should say about formatting. a lot of times people want to throw away USB drives because they're old or they're small, and you accumulate a whole bunch of them over the years, and you're going, geez, this one's 128 gigs, and this one's like 1 gig. Like, what am I going to do with this ancient 1 gig drive? Okay, and you might want to throw it away. You got to be careful, even if you format it, even if it looks like there's no files there, that data is still there, and a good hacker could go in and can still see the data that's there. So formatting is just a very superficial wiping of the drive. It doesn't go deep. Okay, so you say, but I want to throw this out. Well, you know what you could do before you throw out any device that has memory on it? You could take a hammer to it. It's that simple. Okay. Now be careful, of course, because this stuff will shatter or whatever. Okay, but if you take a USB stick and you hammer it, okay, and you crack those integrated circuits in there, it's game over. No one's going to be able to retrieve that. Okay, the amount of damage you do by just smashing it is enormous. Because think about how small the components are in there, okay, like the transistors and all that. So, one good smack by the hammer, a couple good smacks by the hammer, and this thing is done. So, whenever I throw things out, I will, I'm almost always throwing out just USB sticks. I'll just smack them a few times with a hammer. And, I've got glasses on, so, just watch it that you don't shatter stuff into your eyes. But that's it. That's all it takes, okay? And, don't think that you could just format it or just drag stuff to the trash and then empty the trash and then throw it out, that it's a secure deletion. That is not a secure way of deleting it. There are programs that do secure deletion, like Shred or whatever, but the hammer method is good enough. So there it is, okay? Now, the important thing in all of this is choosing a good password. Okay, so choosing a good password and not forgetting it. All right, and well, let me do the not forgetting it first. These encryption algorithms, the ones that we use today, they are so good that if you forget that password, no one in the world is going to be able to decrypt that drive for you. Okay, so suppose you use File Vault and you've encrypted your laptop and you forget the password and you go, oh, you know what, I just can't remember this. I'll bring it back to the Apple Store and have them fix it for me. The Apple Store is going to say, we can't do that for you. Okay, we cannot decrypt this for you, even, using all the computing power we have. It is possible on the most extreme. What people do is they have these techniques. It's called brute force, where they'll just try one password after another. So this is not a human being trying one password after another. It's a computer program trying one password after another, after another, after another. But if you've got a good password, it's not going to happen. It could take years. Imagine a computer dedicated to trying to get into your computer, just year after year after year, trying one password after another after another. So it's pretty much game over. Okay, so one, you don't want to forget the password. You could legitimately write it down and then store it in your, say a file cabinet or something like that, and that's fine. But there's another thing that these encryption programs do for you. They'll give you what's called a recovery key. And what you can do with the recovery key is you can put it in a file, print out the file, and then store that too. If you forget your password, you can also use the recovery key. Okay, so there's usually two ways in. But if you lose the password and you lose the recovery key, it's game over. The data is there, but it's unretrievable at that point. Okay, so there's one thing. Don't forget your password. And the other thing is you got to choose a good password. All right, if you choose a really weak password like DOG, like dog, okay, this brute force technique that I mentioned earlier, I mean, hackers will try it. They won't do it for years, but they might try it for an hour. And would a good password cracking program hit DOG within an hour? It would. It probably wouldn't even take an hour. Within a few minutes, they would find that your password is dog, D-O-G. Okay? And you say, well, how do you make a good password? Well, people used to say the technique for creating a good password is to make it like, mix upper lowercase letters and things like that. That's actually not that good, okay? So I'm going to show you a slightly better technique for creating passwords, all right? So let's go to this site right here. Nope. There we go. No, sorry. There we go. Okay. This is a XKCD is basically a comic strip, but it's aimed at computer technology. Okay. So this is a pretty telling comic strip right here. So we got the old way, the top three panels here are the old way of doing passwords, okay? So the old way of doing passwords was, like pick a weird name, like troubadour. Like, what the heck is a troubadour? It's basically like, a wandering minstrel in the Middle Ages. Like, who would have even known that, okay? So you take troubadour, and then you do like common substitutions, like you use a 0 instead of an O, and like a 4 instead of an A, and then you use upper and lower case letters and things like that, okay? And you do that, and it's very easy for a computer to actually crack this. It doesn't take that long to crack, a password, which is just one word long, no matter how many substitutions you did or whatever. Generally speaking, a password like this can be cracked in about 3 days. Okay, and now what you've done is you've created a password which on the one hand is very easy for a computer to crack, but very hard for you to remember. Like, oh, what's this? Oh, something just appeared there. So, very hard for you to remember. So on the one hand, it's, easy to forget because, you're not going to remember this weird spelling for troubadour with all the substitutions of everything. And yet it's easy for a computer to hack it. The better technique is what's known as a passphrase. You say, well, what's a passphrase? A passphrase is basically at least 4 words, but more. Take 4 random words, okay? So in this example, it's like correct horse battery staple. And you go, well, that's absurd. Like, what does that mean? You're right. They have to be 4 unrelated words, okay? So correct horse battery staple. And it doesn't matter whether you put spaces in between them or not. Like when you're typing in your password, you can have spaces in the password, okay? So you can put them all together or put spaces in there. It doesn't matter. And so, you take 4 of them like this. And if they're generated such that they are truly random words, it turns out that this gives a lot more bits of entropy. Entropy is just how complicated the password is, okay? It's much more complicated so that it takes like 550 years for a computer to crack that passphrase, okay? So cracking it is hard, and yet it's kind of easy for humans to remember it. I know it's kind of a crazy password, okay? But if you say it enough times, correct horse battery staple, correct horse battery staple, you learn these 4 words, and it's easier to remember certainly than this password is, but it's hard for a computer to crack it, okay? When I say crack, it means like, just try the same password over and over and over again until it finally hits the correct password, okay? And so you could see that, this crazy troubadour here, a computer cracking program could do it in 3 days, whereas this passphrase would take 550 years. That's quite a difference, okay? That makes the difference between whether, someone's going to get in or not, okay? And conversely, this troubadour is hard for humans to remember because you get confused about like the substitutions that you did, and yet this passphrase is easy to remember. Now, this comic strip suggests 4 words. 6 is probably better. Okay, it's probably 6. You could be really safe. Okay, so most of my passphrases are 6. All right. The trick, the only hard thing, is that they have to be unrelated words. And so you say, well, geez, how am I ever going to get unrelated words? And the answer is you can use a passphrase generator. So this site here, fermilab.ch, that's in Switzerland, okay? It's basically a passphrase generator. There's a lot of them out on the internet. You just Google for passphrase generator. And what you could do is you could say, okay, this seed is just like a random number to like kind of generate all the random numbers, okay, like that. And then down here, you can say, look, I want to generate 20 passphrases. Not that you're going to need 20 passphrases. You're going to pick one of the 20, and that's the one that you're going to use. But you could generate 20 of them, okay, and then pick your favorite one. You're going to say, how long is it going to be? You could say, well, you know what, I only want it to be 4 words long, or you could say I want it to be 6 words long. Okay, so how many words is it? And how many bits? Bits just means complexity. Okay, and at 88 bits, the complexity is so high that you really don't have to worry about this passphrase ever getting cracked. Okay, and then you hit the generate button, and what you could see here is that I'll do it again. Here, let me do a new seed and hit generate, and you can see that it just created like a whole 20 rows of 6 words each, and these are your passphrases. And you can look down here and you can go, you know what, I kind of like this one. All right, it's a bit funny. It's See, what does it say? It says Sunlit, Scabby, Peter, Assay, Runt, Baddock. Okay, a little bit weird, but maybe you can find another one that is a little easier to remember. Maybe like this one: account, slur, flying, minstrel, frying, and deckhand. Okay, so you just memorize those 6 words, and there's your passphrase. Okay, and at that point, you can, once you've got that passphrase memorized, you can even write it down. Just store that piece of paper somewhere safe. Okay, you don't want it anywhere in your laptop because you don't want anyone else to see that passphrase. And then you can just memorize it and then use it, and there you go. There's how you can keep your information safe. Okay, so that's it for the lecture. A lot of these concepts, they're not that hard, but they are, unless you see them, a lot of people, unless you see what's going on, you don't really see what virtualization is and all that. So I've got another video after that you should watch after this, and it's got 3 demos in it. Okay, the first demo is running BlueStacks in Windows 10 to emulate an Android. Okay, and in that one, I basically install a program. I install BlueStacks, and then I install Clouds and Sheep again. Okay, and in my second demo, I do VirtualBox, and I'll do Ubuntu Linux in that. Okay, and I'll also show you how to encrypt in that one. Okay, and then the last one is basically I'm going to do BitLocker in Windows 10, and I'll show you how to encrypt a USB drive. Okay, and I recommend that just on your own, because I'm not going to test you on this, that especially if you have Windows 10, it's pretty safe. Try encrypting a USB drive. Okay, by the technique that I had. Okay, don't do a USB drive that has important information on it, because in case you do something wrong. But it doesn't hurt to try it. Just take that USB stick, plug it in, and then go through the steps that I show you in the demonstration, and then take it out, and then bring it to a computer at the school. If you have to use a computer at the school, and plug it in, you'll see that it asks for a password before you can get at that onto the files of that USB stick. Okay. All right. There you go. I hope this is more practical and useful for you. It gives you an idea of hardware that's out there and why you might want to choose one hardware over the other, operating systems that are out there and what they do for you, and the compatibility issue between applications and and software. Sorry, application and the operating systems, and finally, how to do encryption. Okay, bye-bye.